Great. So our next speaker will be Louisa Grifu, and her talk is on differential powers in mixed characteristic.
Great. Well, thank you so much to all of you for coming, and to Luis and Jack for the invitation to speak here. It's so great to be here. I'm just disappointed we couldn't all be together in Buenos Aires. Maybe I'll still count this as my first time in South America, even if it's only virtual. So I want to tell you about some joint work with Alessandro Stefani and Jack Jeffries. And of course, this is a story that begins with differential operators, since that's the topic that brought us all together here today. The definition has already appeared at least once this morning, and I think we're all familiar with it. One definition that hasn't appeared yet is a definition of differential powers of an ideal. So if I have some A algebra R and I take an ideal in R, I can define its nth differential power as the ideal of all the elements in my ring that are taken inside of I by all differential operators of order up to n minus 1. And just in case maybe you've never thought about this, this is not a typo. So this is a little off from the n over here on purpose. Right, so it's the things that are sent into I by the elements in R, okay? And there are many reasons why you might care about differential powers. For example, because you care about differential operators. But one reason that I personally got interested in this is a classical result of Zariski and Nagata that I'm gonna write here in a slightly more modern fashion, sorry. So let's say that I take a perfect field and that I take a polynomial ring over that perfect field. And let me say that I take a radical ideal. Then all its differential powers are exactly the same as the symbolic powers of I. And just in case you haven't thought about this in a while, so the n symbolic power of an ideal is what I get when I take the ordinary power and I localize at each of the associated primes, which under my assumption are the minimal primes, and I can track back to R. So I wrote down a primary decomposition for the ordinary power, and I collected all the minimal components in that decomposition and threw away the embedded ones. So maybe writing this in a more classical fashion, this is the intersection of all the powers of all the maximal ideals that contain I. So this is saying that this differential power is the set of elements that vanish to order n on the variety that I defines. Now, what I want to talk about today, my title is something about mixed characteristics. So I want to talk about a version of this theorem in mixed characteristic. So I want to replace this perfect field with maybe Z or a DVR. So here's the first simple example, or one of the first simple examples you would write. Let's say that I'm over Z is drawing one variable, and I'm going to consider the maximal ideal generated by 2 and X. And if you know anything about symbolic powers, you'll know that the symbolic powers of a maximal ideal are all equal to the powers. But if I want to compute the differential powers of this maximal ideal, I'm going to want to, for example, see what is the differential operator what does a differential operator do to 2? And my differential operators are Z linear. So they're going, whatever the differential operator I take is, of whatever order, it doesn't matter, it's always going to take me back inside of my maximal ideal. So this is telling me that 2 lives inside every single differential power. But of course, it does not live inside every symbolic power or power. So you might think of this as a feature. Maybe for now, I'm going to treat it as a bug and try to fix it, in the sense that I want to add in something to my differential operators that's going to see what's happening in this arithmetic direction that the differential operators don't see, right? And what I really need, maybe let me say from now on, is going to be Z or maybe let me write it here, AZ or some DVR with uniformizer P, where here P is a prime integer. And what I'm going to need to do what I want is this definition of P derivations. So these are maps from R to R that satisfy these three conditions. And you don't have to remember these three conditions for the rest of the talk. I just wanted to show them for completeness. But I'm asking for three things. I'm asking that one be sent to 0. And I'm asking for some rule about sums and products. And the rule about products should remind you of the Leibniz rule in some sense. But it's sort of a Leibniz rule is kind of twisted by P powers. And there's some extra term. And then I also want to point out that these maps are not additive, right? At least I, as an algebraist, a community of algebraists, I'm used to thinking about additive maps, but I get this funny extra term. So these are maybe a little weird the first time you see them. So let me tell you about a way to think about them. So if you have a P derivation on R, that's precisely the same data as giving a map phi that is a lift of the Frobenius map on R mod P. So what's a lift of a Frobenius map? That would be a ring homomorphism that sends elements to their Pth powers, plus maybe something inside of the ideal generated by P. And if you look at this sort of correction term, this delta, and you just focus on what delta is, and write down the conditions that you need to get this map phi to be an actual ring homomorphism, the three conditions you would write, rewritten in terms of delta, would give you these three conditions up here. Okay. So another thing that perhaps you'd notice right away is that we don't always necessarily have lift of Frobenius. So we don't always necessarily have P derivations. So what I'm going to talk about today are rings that do have P derivations. And so in particular, the ring of integers is such a ring. So over the integers, when I go modulo P, the Fermat's little theorem tells me that the Frobenius is the identity, right? So that means that the identity map is a lift of Frobenius. And in fact, you can show that this is the unique P derivation on Z. And in fact, if you take any Z algebra, and if it has a P derivation, its restriction to Z is precisely this map that I just described. Now, for other examples, if you take a complete unramified DVR with perfect residue fields, you also have a P derivation. And whenever you have a ring with a P derivation, and you take a ring of polynomials over that, infinitely many variables, you also have a P derivation. So this definition should somehow vaguely resemble things that you want derivations to satisfy. And in a way, one important thing that's going to make these be the maps we were looking for is the fact that they decrease p-adic order in a way that differential operators did not. So by that, I mean that if you take something that's a multiple of p to the k, not p to the k minus 1, you get something that's a multiple of p to the k minus 1 and not p to the k, modulo p to the k. But so with all this, I'm going to define a mixed differential power where I'm going to mix in together the usual differential operators plus this P derivation. So the mixed differential power of an ideal I is now going to be the set of elements that is taken inside of I by, well, first of all, I'm going to apply differential operators of various orders. And then I'm also going to allow to apply P derivations. So in fact, I'm going to take my chosen P derivation and I'm going to allow to raise it to A. So I'm going to think of this, this composite as sort of a mixed differential operator of order now A plus B. So I'm going to want that order be at most n minus 1 to be in the nth mixed differential power. And with this definition, I can now tell you a theorem with Alessandro Stefani and Jack Jeffries that we proved that if you have a localization of a finitely generated smooth A algebra, where A is, again, Z or some DVR with uniformizer P, and you take a prime ideal, you sort of have two options. Either your prime really doesn't intersect A, in which case we're sort of back in the old situation. So this shouldn't be a surprising result. It's the same theorem we had over a field, and it's essentially the same proof. It's understanding that the old proof works. Then you do get that the symbolic powers are described by these differential powers. And then the other possibility is that you do have something in A, so you're going to get either your uniformizer P or some prime P in the case of Z. And now in this case, we saw that example in the beginning with 2, right, where it wasn't enough to consider just differential operators. They actually give me something bigger than the symbolic power. So instead now I'm going to take these mixed differential powers. But this is modulo some fine print that I very cleverly already wrote out here in orange. So of course I need my ring to have a p derivation for this to even make sense, what I just wrote down. And then I'm going to want the extension from A mod P to the localization, to the fraction field of the localization to be separable. So for example, if A mod P is perfect, that's a good situation. So this is I guess it's not officially a theorem of 2020, but is from a few years ago, really. But what I want to tell you for the rest of the time is I want to tell you of a recent application of these types of ideas. And it's going to be an application to a situation where even over a field, the differential powers are no longer the symbolic powers, but I'm going to use differential operators and ideas about differential powers to prove something about symbolic powers, or I'll tell you that you can, really. I won't have time to show you the proof. And then I'm going to tell you about a mixed characteristic version of that same result. So this is a story that begins in the 40s with the Theorem of Chevrolet. If you have a complete local ring and some decreasing family of ideals whose intersection is 0, then in that situation, take your favorite power of the maximal ideal, you can find some element of your family inside of that power. So really, there exists some function that's going to encode, which element of my family I'm going to get. And I want to focus on this special setting where this decreasing family of ideals, of course, is symbolic powers. And in that situation, Hünicke, Katz, and Validasti gave us an amazing version of this, that there actually is a uniform version of this. So there exists a constant C that doesn't depend on the ideal that you chose, such that the Cn symbolic power is actually contained in the nth power. So this is actually saying two things, right? It's saying there's some uniformity, some independence of the ideal, and that the function up there is in fact a linear function. So what I want to do is I want to make this concrete. I want to find concrete bounds on this constant C. They just told us it exists. And notice that if I solve things like this, I'm sort of saying, I'm giving lower bounds for the degrees or the ematic order of elements in the Cn symbolic power. And the degrees of these things are often difficult to compute. So the special case of regular rings already follows from something else that I'm also going to call the Zariski-Nagata theorem. So in the case when R is regular, you actually can take C to be 1. So the n symbolic power is contained in the mth power. Okay. Now, when your ring is singular, C equals 1 no longer works. What C's could you choose? So first, let's talk about what happens over fields. So there's a survey on symbolic powers with the Landau and Alessandro Stefani and Craig Hünicke and Luis Núñez-Betancourt that in particular contains some original results, and this is one of them. And what the result says is that if you have a direct summand, actually a graded direct summand of a polynomial ring over a field, and you look at the homogeneous prime ideals, the constant you want to take is just the maximum degree of the algebra generators of your graded direct summand, okay? And this is a situation where the proof here relies on differential operators and differential powers. But as I was announcing earlier, I'm now working over a ring that is not regular, where I don't know the symbolic powers or differential powers. In fact, they probably are, they usually aren't. But you can still apply differential operators to prove this. And while I don't have time to give you a proof, I have time to tell you about the ingredients that go into this. So let me tell you about some ingredients that are differential operator flavored. And these are essentially all the ingredients you need. So I have a graded direct summand of my polynomial ring. So it has a splitting that I'll call little f. So one of the ingredients I'm going to need is a result of Alvarez Montaner and Craig Hunicke and Luis Nunes Betancourt, who showed that if you take a differential operator over the polynomial ring upstairs of whatever order, and you compose it with your splitting, then you're going to get a differential operator up to the same order downstairs in your graded direct summand. And then, even though the symbolic powers are not differential powers, they're at least contained in the differential powers. And that somehow is enough for what you want to do. And then you also use, I forget for a moment, there's a different ingredient I want to tell you. Oh, yes. The other ingredient is something happening that the actual Zariski-Nagatev theorem, that if you look at the maximal, the homogeneous maximal ideal upstairs, so over the polynomial ring, then even though I took any field, not necessarily a perfect one, it's still true that the symbolic and differential powers are equal to the ordinary powers. So the idea for doing something like this in mixed characteristic is to try to copy these ideas and to cleverly replace the differential powers with the mixed differential powers when necessary. But there's a catch. The catch is that even though I have a p derivation upstairs, I don't necessarily have one downstairs, or I don't know that I do. And so you have to sort of work a little harder to copy these original ideals to do this. So let me just tell you what the result is. And then I'll show you just quickly what one of the main ideas is. So now I'm over a DVR with uniformizer P, perfect residue fields to guarantee I have a P derivation upstairs. And I just have a subalgebra that is graded, generated by homogeneous elements Fi. And I'm going to consider two situations. I'm going to take primes first that are contained not in the homogeneous maximal ideal, but even in the ideal generated by the Fs, okay, by the algebra generators. So some nice homogeneous ideal. And in this case, I'm going to require, as we did in the field case, because it's sort of the field case, that I still have a direct summand. And then the theorem is essentially the same, is that the dn symbolic power is contained in the n to the nth power, where d is, again, the maximal of the degrees of the generators. And the other situation is where I have a prime containing the homogeneous maximal ideal that contains P. So let's say P is in here. And now I need to ask only that when I go mod P, that I have a graded direct summand. And then the theorem, shoot, I'm going to correct something. Okay, the theorem is, again, that I have this containment. But I should say that in the previous case, I could do better than m to the n. I could use this ideal generated by the Fs, right? So here, m is what I get when I actually add in P. Q is the guy when I don't have P in yet. And since I have a few more seconds, let me just show you. So first of all, the theorem written again. But as I was saying before, I'm going to piggyback on the P derivation upstairs. So I'm going to define sort of a different type of differential, yet a new version of mixed differential powers that's written down here. It looks a little technical, but it's sort of the way you go around things, and then things work out. So now I am out of time, so thank you so much.
Thanks. Are there any questions?
I do have a question. I wonder if you have some definition of differential signature in this setting, and if there's something about singularities or.
So such a definition has not been made yet, to my knowledge. Maybe Jack can say more, since he's really the expert on differential signature. But that does sound like a good idea. But if I remember correctly, the definition of differential signature doesn't come directly just from differential operators, right? There's some more business going on with these. Am I wrong?
You can define using the differential powers, right? So
you can. Oh yeah, okay. Then in that case, maybe you would take it with the mixed differential powers.
Mm-hmm.
And
so the question is, what would be being positive or something like that?
That's right. That's right. That sounds like a good question. So honestly, so there's now been a few other results of the sort, you had something over a field where you use differential operators, and now you throw in p derivations and you kind of get a similar result, right? So to me, it wouldn't be surprising, just from a philosophical point of view, right? Not quite a, I don't know how the math details would go, but it wouldn't be surprising to me if there was a similar statement to the one over fields. But I don't know. It sounds like a good question.
And so maybe the most direct definition that you would have in mind would involve like mixed differential powers, where you have a p derivation on your ring already.
Mm-hmm.
And part of the catch of that is that it's not really well understood when we do, which I guess is the motivation for this green definition, right?
That's right. That's right. Yeah, it's in. If you notice the slide where I wrote down cases where you do have a p derivation, I mean, there are other exciting situations where you have it, but it's in general not very well understood when you have one or not. But I mean, on the other hand, there are things like the green definition that go around not knowing if you have a p derivation.
Mm-hmm.
So it's possible, like for things like direct summands of polynomial rings, that you could use something like the green definition. I don't know.
Okay.
Are there any other questions? I was wondering, and I might have known this at some point, are there other situations where there are explicit formulas for this constant C that are known?
Oh, not very many. I don't think so. Yeah, I remember thinking about this recently, and I haven't seen other results that are computing this constant explicitly. Maybe they are out there and I don't know them, but I don't know. I think in a priori, I would expect it to be difficult to compute this constant. And maybe I should say, in this situation, we do know this is sometimes best possible, right? We have examples where this is the best you can do. But in general, even just giving a bound, I think is hard.
Thanks.
I mean, okay, maybe I should add something else. If that there are variations on this problem, right? Here, we're just trying to find things inside the power of n. If you instead know something about the containment problem, which is asking about things like this, right? And if you there are situations where there exists a uniform constant where this is true. Then if you knew this, then then you'd be in business, right? But I haven't this problem that I'm talking about today, I think it has been less studied in this explicit sense than the containment problem. So I'm sorry. So that would have been the right answer, right? Yeah, situations where you know how to solve the containment problem. Yeah.
And I have a question. Is C equal to 1 is a characterization of regularity?
Oh, good question. Good question. Is it a characterization of regularity? I have to think. My intuition says yes, but I couldn't tell you why right away. So I'm actually not sure. Good question.
Okay. Okay.
Any other questions? Okay, well, if not, let's thank you, Louisa, again. And we'll start again in about 4 minutes.